Hello, welcome to everyone. I am Harish Konanki. I am happy to present my research today on industrial design for dosing and weighing systems in the process industry, a model-based approach for the 18th IEEE International Colloquium on Signal Processing and Applications. Let me tell you how we are going to proceed further in the presentation. I would like to give you a short introduction to research focus of this paper and would like to present you the physical model of the bulk material handling equipment considered for this research. Then I would be presenting the methods that I had been followed for calibration and validation of the physical model. And then I will introduce you to the modeling and proper validation of the controller. Finally, I would like to give you some factual results and would like to conclude with what has been achieved during this research. Generally, we notice that the implementation of a stable industrial controller has many challenges, such as it involves in excessive tuning of the controller parameters and testing at various test scenarios and conditions. Even though one could succeed to develop such a controller with considerate efficiency, the same cannot be promised when the machine handles various materials with volatile properties. It is the same focus for us with one of the bulk metal equipment of our focus, which is gravimetric plate dosing conveyor. However, due to the availability of robust simulation softwares, we make use of it in this research to focus on developing a model-based simulation framework for real-time simulations, which would also help to assess the machine performance testing with various materials. In addition, our proposed solution is to develop a novel-based approach for the evaluation of controllers' performance, about which I am going to discuss later in the presentation. So now let us start with the physical modeling of the gravimetric plate dosing conveyor, which is going to be made the main focus. The gravimetric plate dosing conveyor is a type of conveyor where the conveyor is found by metal plates attached to a chain link. It is designed in such a way that it handles various bulk materials from homogeneous to non-homogeneous. A sophisticated weighing system is designed to measure the mass per length of the conveyor to determine the output mass from the conveyor. It is so important to do so because the machine is going to be operated in energy intensive industries where the output mass flow has a critical role to play. Thus, the output mass flow rate should be controlled very accurately. Two research stations have been established in such a way that each plate of the conveyor rolls on it so that the load cell can capture and calculate the weight or mass per unit length. Using the other dynamic properties of the system and from the Newton's laws of motion, one can easily determine the output mass flow rate. As you can see here, the difference of mass coming onto the measuring length and going out of the measuring length plus what has been lying there gives us the actual mass on the measuring length at each iteration. However, this is a raw calculation under no influence of controllers, but under a control architecture, one can eventually regulate the mass flow rate by controlling the speed of the conveyor and the input material flow rate, which will be discussed later in the presentation. But for now, let us keep our focus on a validation of the current physical model. As you can see here, this is the physical working model of a gravimetric weight dosing system that has been used for this research. Considering the same material at same operating conditions, various tests were conducted on the physical model and measure recordings were taken at various speed ranges and as shown here. As you can see, it is evident that the measured mass has a direct influence on the conveyor velocity. Optimized numerical model of the machine, a statistical model from the real world measurements is introduced, which can be interpreted as a necessary calibration of the simulation. For this work, three different distribution types are considered: normal, log normal distribution, and viable distribution. So the collected empirical data from each test run is used to generate the distribution curves that best fit the data for generating the random error by knowing the mean and standard deviation of each distribution type. The figure here provides an example for fitting process for a conveying velocity of 40%. Here, the original weight measurement data is shown as a histogram in green color. As some of the distribution types only allow the modeling of positive values, the complete data set is shifted a bit. This process is subsequently repeated for all speed datasets as captured on the machine prototype. The parameters of each fitted and shifted distribution type at various velocities are shown in the table here. Considering various criteria such as Bayesian information criteria or Akaike information criteria and the statistical value of sum of squared distances, the Weibel distribution has chosen to the best fit the data and can be used for statistical model development. On the above plotted distribution curve based on the empirical data, there is a certain influence on the actual mass based on the speed of the conveyor. These curves have this shift of mean value and different standard deviation values for each different velocity, which means this kind of behavior can be modeled within the simulation model by adding an offset as a function of the speed and noise, where the standard deviation is also a function of the speed. To mimic the behavior of the real system, it is not only important to consider all influences on the system itself, but it is also vital to take possible variations of the transported materials into consideration, especially since the applicational background of this work deals with the usage of the system model for process applications such as cement manufacturing. The figure here provides a visual representation of bulk materials with varying characteristics which are usually used with the described mission. Let us now move on to focus the modeling of the control loop architecture. The control loop here illustrates the mass flux controller where, based on the current estimated mass flux, the actual conveying speed is controlled in a way that the mass flux meets a predefined mass flux set point. The principle of closed loop can be explained in such a way that there is a direct feedback from the calculated mass flux to the desired mass flux to find out the actual deviation. Suppose there is a difference between the actual mass flux and the reference set point. The conveying speed can be adjusted continuously relative to the current speed to ensure less deviation from the target mass flow rate. Similarly, the second control loop structure as shown here consists of a plate load controller, which is useful to stabilize the plate load by adapting the incoming mass flux. In the second control structure, a feeding storage and transport system, typically called a pre-feeder, is controlled in a such a way as to maintain a desired mass on each plate by adjusting the pre-feeding factor, which influences the incoming mass flux. As it was stated in the introduction, the model-based controller parameter tuning shall be evaluated by using the developed simulation environment. So let me discuss some of the findings of our research. Here, different test cases were developed and validated accordingly. In the first scenario, typical set point variations for the mass flux are tested and evaluated. As shown in the figure, the model-based tuned controller can actually perform mass flux set point adjustments with very small deviations regarding the actual mass flux and plate mass. In a similar way, the second scenario deals with the inclusion of the adaptive plate mass set point procedure. As it can be seen, the advantage of having a relatively stable conveying speed can be achieved through both controller architectures. The third scenario deals with the introduction of the volatile bulk material characteristics. For this test case, where the actual material characteristics are changed at defined times according to their statistical density model. As you can see in the figure, the material changes at 800 seconds and 1200 seconds in a way that the bulk material density and the humidity are increasing over time, and the actual standard deviation of density is also increased accordingly. However, it is now time to compare the data from the simulation model with the prototype. This helps to assess the performance of both simulation and real-time model. At first, the case is operated at various speeds with no mass on the conveyor. Here, 2000 samples were taken. Since the test run lasted for 100 seconds with a step size of 0.05 seconds. Even the simulation also ran with the same similar step size of 0.05 seconds to avoid the mismatch between the data points from the simulation to the prototype. As it can be seen in the figure, the comparison shows that the simulation is also able to mimic the real system with a satisfactory precision. Based on the controller parameters found in the model-based tuning, the real prototype was operated with different bulk materials and provided the proposed controller optimization strategy. Thus, to conclude, to carry out the research, a novel-based simulation model of a gravimetric plate dosing conveyor is created and developed a control loop and developed a closed loop control architecture. The robustness of the simulation helps an effective design of the system and closed loop controller architecture optimization. The simulation has also provided a better way to compare the test results with real-time test cases and helps to verify and validate the performance comparing with the real model. Hope you found it interesting. And finally, I would also like to acknowledge all the sources of information that were useful during the research and would also like to thank our sponsors of this research. And I would like to also thank you all for your patience and attention. Thank you.